Well, thank you very much for the kind introduction. I'm actually going to go one step further than paper and electronic notes. I'm going to try and do computation live with a test version of our software, so you have to wish me luck. All sorts of things may go wrong, but I like high-wire acts. I'm really going to talk about a range of different things, but what focuses this is the idea that nowadays we largely have computation available to us ubiquitously, in time and in space, so to speak. Everybody has huge amounts of ability to compute. And the question is, what does that affect about the future of the sector, higher education, about the technology, about the humans? How does that all fit together, and what should we be looking to do as we progress through the next few years? So really I want to cover various things. Where does this apply? Departments and projects. Used to be just the physics department and engineering who were worried about high-powered computation. Now it's the English department, computational linguistics, other things. How does a system and per student data, everything to do with data. Data is big news, both in what people do with it, but also in how universities and other places can manage themselves. How assessments work, and the best way to provide these services. And I'm going to come to the end in the last few minutes about a passion of mine about the subject that students are actually learning, particularly around maths education. So I want to zoom right out for a moment. Computation, the idea you can logically compute results, is a very powerful idea. And it's so powerful that we've kind of forgotten that it's not that old that it could be used effectively. And so one question I want to ask is, we're at a certain place in computing things. How much further can it take us? What's so far succeeded, what's failed, and what can we do to broaden that use? So I think you could say that what's worked well so far is traditional computation domains, things like, astrophysics, planets going around the sun. That's worked pretty well for a long time. Scaling up things you did on pencil and paper 50 or 100 years ago worked okay. Well-structured things. Most of the places we were doing things with computation up until 10 or 15 years ago, very well-structured problems. Engineering problems. There's you fix things together. Simple specify questions of data. What's still not so good yet, but coming? Fuzzy questioning. Medical things, social sciences, things where the question isn't as clear-cut as, how long will it take Mercury to go around the sun. Rapid deployment of new ideas. It's quite hard to get new kind of pieces of computation out and being used. We'll talk more about notebooks and things like that which help with that. Communicating with computation is also part of that picture, and the utility of sort of modern data structures. It's amazing how much is rectangular in this world in terms of data structures, and I'm not sure that really is the best way to make things work. So my basic message is there's actually a long way. We've gone a long way with computation, but there's a lot further to go. And of course, the big field that's emerged in the last few years around computation is data science. And data science is now achieving huge numbers of things that even a few years ago we thought weren't possible, although again, there are some issues there. So something I sometimes describe myself is sort of my day job is trying to make computation for everybody. And in a sense, the way I see doing this is try to build technology that is as automated as possible, but at a high level of automation. And the sort of evening job is to try and get the people adjusted to this new computational era. Because it sort of seems paradoxical, right? It seems like if you make the thing as automated as possible and easy to use as possible, you shouldn't need to adjust the people. Well, there's a certain sense of truth in that you can go where you wanted to go before, but better with better computational automation. The problem is, once you do that, then society wants more. We want to go further. And then the question is, are the people equipped to do that? Given that you can now compute anything you want to compute, are we all equipped to know what questions to ask and to how to work with that so that we optimize the use of this technology? So that's why I don't think it's actually contradictory that I think in both these directions at the same time. And I suppose another way to look at this is, as we go forward in all use of computation, what's the best optimization between the human and the AI? What is it that humans should be doing in future in all areas of our jobs, our society? What is it that we should leave to increasingly sophisticated AIs? And I think if we think along those lines, then we can start to develop the directions in which we ought to go. I thought I'd start with a demo, and this is a thing we built with our technology stack to try and give an example of kind of putting computation, AI, and data together for everyone. This is, as you see, a video of my computer, and what it's done is we've trained it to some machine learning, and it has correctly identified that I'm a person. So that's kind of a good start. Let me see. It will probably do some pretty weird things. That is pretty weird. Oh, I guess that's Neptune is the, I guess that must be the edge of your logo. And swimming cap, and I'm not saying this is necessarily well trained. Let's see if, beer glass, well that's not too far. Oh, bottled water, well we're getting there. Anyway, the point of this was to show two things. Firstly, that I might just be an everyday user. I might have nothing explicitly to do with computation. I might use something to identify images. So that's where computation comes to people who are not necessarily that technical. The second thing was, on the technical level, it took us about a month or under to build this whole system. So that's what I mean by trying to automate every layer of the technology stack so you can actually put something together with the linguistics that figured out person, with the machine learning, with the video and everything else. And that's the kind of thing that one can do with modern technological setup. So how do we achieve this goal I have of computation for everyone? And I add in here highest level and insightful. I mean, it's all very well for us to compute stuff, but the question is, do we get decisions and answers and progress out of that? Or do we just do it because it's there? One thing I think is important to think about, and I mean this is true in all walks of life really, it's kind of like you want what I call a multi-paradigm approach. What do I mean by this? I mean that you want to take lots of tools in your tool set and use the best tools for the job. Seems pretty obvious. But what often happens when new technologies are emerging is you end up with one tool set people are very excited about at a given point in time, and you focus all your energies on what that tool set does, and you forget about the other tool sets. So right now, machine learning is big news for everyone in data science, and machine learning has lots to offer. We have lots of great machine learning too. I think machine learning is a very interesting direction that much can be accomplished with. But it's not the only way to do computation. There's all the algorithmic computation that's been done for many years. There are numerical computations. There are many other areas. And the trick in this is to remember those areas and to approach not just the one paradigm of, for example, machine learning, but to manage to make sure we can use whichever of those tools or hybrid version of those tools is best for the job. And so I'm all for hybridization, so to speak, of different abilities. And I think this comes true when you think about how you present lectures or how you make any educational technology work. You shouldn't necessarily focus on just the approach that's currently exciting. How do we make computation work for everyone? I think the place I always like to start is the interface. How are we interfacing with what we're doing? I showed you a sort of fun interface of the image identify. But let's talk through the other interfaces one works. I sort of think once you've got the interface idea, both to the input and the output, it's kind of letting you plug in what happens in between and figure out how to make that work. And sometimes, of course, what's possible guides what's okay with the interface. So one of the things we've been often working on is linguistic access. So what do I mean by that? Well, if we go off to, let's say, this Wolfram Alpha side, I can type in something like, let's say, ox.ac versus cam.ac. So I guess what I was going to do here is get it to analyze the web traffic, except I've done something slightly, that's strange. It was doing something different before when I did it, as they say. No, I mean UK. I think it's gone off to a different domain, .ac. Is that right? ox.uk.ac. I was meaning to get Oxford. Maybe I've done ac.uk, which is why I'm totally confused. Okay, ox.ac, thank you, .uk, yes, right, versus cam.ac.uk, which I should know from past eons. Since I live in one place and went to the other, I guess I should kind of know. So, I mean, what this did was it basically computed live. It's a little bit small, I'm sorry, but I computed live what happens about, I typed in that, I haven't really said what I want, but it's computed live these pods that is going off live and comparing, the location, the coordinates of those locations in this case, how much traffic there is per day, and I guess it looks like Cambridge is slightly beating Oxford in this particular case, etc., etc. And I can go off now and fire that up in the cloud and get the code, hopefully, that would have generated that. So I'm now linking a linguistic interface, in a sense, with code, except I've managed to move over, with code in a cloud that allows me to regenerate that with different entities in it, for example. So that's just an example of sort of how might one interface with a bunch of data, or in this case, live data. And there are more amusing things one can do, which one wouldn't necessarily think are, so to speak, computational. So if I go off and say, for example, am I drunk? One can get even a computational result from things like this. And we fire up an application here which is trying to figure out whether you put in the parameters. I'm a lot heavier than 140 pounds, I have to say. And it will go and start calculating things about that. And we do. 100 years ago, people didn't calculate things like this. It was just, well, were you drunk or not drunk? Now people actually have numbers associated with these things. That's the modern era we're in. So that's an example of a sort of linguistic interface to data, to information. And actually, I was going to show you another example of that. If you go to Siri and you ask it some question like number of UK students versus US students. And Siri willing. Okay, so that went off to the Wolfram Alpha engine, as Siri does for computational queries, and it's come up with that information, and you can see it's kind of cool that it calculated that live and it showed us the history of that and whatever it thought was relevant. So the fact that you can talk to your phone, actually one thing I'll do extra on this, which I will come back to, the relevance of this may become clear later, but if I do something like solve x cubed plus 2x plus 1 equals 0, and when we're discussing what people should learn to do by hand, I will come back to why I've shown you the fact that I can talk to my phone and get a cubic equation solved. Something that most of our students can't do after years of education. And nor should they need to, but that's the later topic. So that was one type of interface. Next type, what one might call interactive apps. These are what I would call knowledge apps. So this is in fact taking the whole data set of a Middle Eastern country, anonymized of course, and calculating their heart disease risk based on actually querying the data computationally as you're running this. So this is what I would call like a knowledge app, and I think this is very prevalent. The key issue here is how easily can you make these things is one key issue, and it's a particular style of interface that can be quite useful. Now, another thing that's interesting, which has actually come up a lot in the last year or so, is the idea of what you might call a computational research paper. So this is really taking an app like I showed you, or many apps, and embedding them within such a paper and making them computational, displaying code, allowing you to actually go through and sort of try these things as a reader. And I think it's a very important methodology, in a sense, for presenting technical ideas. And you'll see this same thing appears here in a similar kind of way. And it's a more complicated app down here, etc., etc. And the idea that you can actually evaluate things, I'm going to do a rather simple thing, but you can evaluate things within that kind of notebook style, I think is an important way of communicating much, much better. And also for courses, for educational courses, things that you can do real stuff. Now, I talked about how you generate things. So, again, I want to come back to linguistics. So it's kind of cool that you can do things like, I don't know, I interact. I'm going to type this in very sloppily, times, let's say, cos, x squared or something. And let's see whether we can interpret that instead of having to type syntactically in. So linguistics can extend beyond data and can extend to things like programming. And it didn't actually do what I wanted there. it's actually done something different to what I wanted, although not totally crazy. Maybe, I don't know, interactive. Let's try interactive or something like that. See if it's happier with that. But what I wanted to show you is, that's what I kind of wanted here. So what I want to show you is it's taken some linguistics in, and it's actually written a program in a language to produce the output. So we've now ended up with an interactive plot, although actually the interactivity in this plot isn't terribly exciting because it's not stuck an A in a very good place. So let me go and edit this and reevaluate it, and hopefully now if I stick that in, you'll see it changes as I move it. But the point is here that it's easy to make the interactivity, and language is one way to access such a thing. And you can do nice things like let's say cloud deploy of that last line. Let's say, what do I want to do? I want to do permissions. Probably I want to do permissions goes to public, and then I want to say, let's make it a short URL, so URL shorten, something like that. So the point is that it's easy to, hopefully, to get these things out, and that should probably go and publish now a URL, which I can then go and paste into a browser, and you can now, hopefully, go and, if I find a browser somewhere, let's see, there's a browser. If I paste that in, hopefully you should get that interactive application appearing on a cloud, and you can immediately go and work with that. So that's the kind of flow which I call linguistic programming. I think is kind of one interesting interface to how you can get real stuff to happen. Okay, let's talk about data. So I think we all want to get more out of the data we have. And how does one do this? I think most people think they've got more data available than they have, so to speak, good results, good decisions, good answers out of it at this point. And it kind of seems a never-ending problem of trying to get more out of it. And so there are several ways in which kind of one can get further with data. One is search. We're very familiar with that. It's great in the sense it's powerful for eking out existing info. It's not great for generating new knowledge. It's kind of like if somebody already stuck it out there, great. If you want to figure out something new, particularly quantifiable, you're kind of out of luck. It's like telling a librarian to go and find something that's already been written. The question you really want is you kind of want a kind of research assistant who goes out and actually generates the information you specifically wanted. So there's several ways to do this. One is sort of AI curation, a bit like I showed you with the image identify. That's good in terms of the fact you can work with pretty messy existing data. It's not very good in the sense that it doesn't work that well in many domains yet. There are many places where people are trying to use this. Visually it works quite well, but in many areas really, people have probably heard many things on the IBM Watson, for example, is a good example of this, where it's quite hard to get it to work well with the unstructured data. The other thing you can do is to try and work more with the data, set the data up to be computational, and then use a computational mechanism. That's sort of approach we use with Wolfram Alpha. Now, the good news about that is I think you get great new knowledge insights. The bad news is you've got to get your data in shape. But I want to come on to that because I think, data quality is something that actually many of you guys have some control over, much more than in some other sectors. And I think a lot of the data currently is being set up for human readability. What you really need to set it up for is so that things can query it computationally. You don't really need the human to look at millions of data points. You want the computer to be able to do that. And that requires a slightly different setup of the data, and I think can be done very nicely to allow the sort of computations I was showing. So here's something that is fairly structured, but kind of cool that one can do it these days. So I'm going to look up, hopefully, a sequence in the human genome. And I'm picking the length, so hopefully we'll get something that matches that, but not too many, and we shall see. And the idea is it's now looking through, there we go. So these are all the places in the human genome that particular sequence matches. Now, if you think about it, it's pretty amazing. I don't know how many years ago it was that they thought they wouldn't manage to sequence the human genome. Now I can look it up on my laptop, and I can match it in a few seconds. And this sort of requires lots of pieces to come together, but piece one is the idea that the data has to be in shape for me to be able to compute and do my sequence analysis on this data. And so that's kind of an important element in our view. Maybe in 30 years' time, 20 years' time, all the computers will be so smart they can really pick up any data and do really smart things with them. I think it's going to be some time before that works in all these areas. So where are there data assets that are structured? Well, there are ours. We've structured a lot. It's one of the things we do. You can go through and pull these. These all come through all of our technologies. But I think perhaps more interesting is there's all the higher ed R&D. I think it's a good requirement of higher ed R&D to have nice structured data that comes out. Not just data that's available, that's a good start, but data that's ready to compute from. And that hasn't always been the case, and I think is a real growth area for the use of that. In a sense, to be able to use the R&D. Opposed to reading a paper about it, it's good to be able to actually use it immediately. There's also sort of what I call higher ed individual data. Data on, for example, students individually and how one can better use that for assessments and in other ways. It's kind of a crazy system. You think about how assessments work traditionally, particularly in schools. We have the students sitting there for years. We then decide we're going to examine them for 2 hours or whatever it is, and we throw away all the data about them up until that point and then make the assessment purely on the 2 hours in which they did their exam. This doesn't seem like the smartest thing to do. And I think this is true throughout. And part of the problem is what I said about earlier. Much of the data is quite fuzzy. And therefore, you need quite high-powered computation to deal with fuzzy data, and that hasn't always been possible. And then there's system-wide higher ed information. I looked up some very basic stuff a moment ago about number of students. But, there are many other systemic things that I think can be used to decide policy, strategy, and one can want to query those things better. The thing one can definitely say is that the value of sort of computational knowledge is much greater than dead information. It's a bit like sat-navs versus maps. You can go a lot further with sat-navs and do many new things that you couldn't do otherwise, and it really is worth getting the data in shape. And one of the things we've been trying to do is set up data repositories to allow different kinds of data to be, in a sense, to give an open repository for people so that they have a certain quality of computational data that can be entered. And there are possibilities to make these private versions of these as well. But I think this is a start to helping people align their computational data. And the way I would also think about this and how you use that is that currently I would think about how, in a sense, we have data collection, we have a bunch of technology, and then we have an expert to interpret or to work with the data, a data scientist or somebody like that. The way we want to set this up is to have data collection, then a computable layer of data, in a sense, in the way I've described. And then all sorts of people can get access to that, whether it's through notebooks or linguistics or just direct APIs. And that's really the ideal setup you want. You want your researchers or your educators to be able to pull that very, very easily with those different interfaces depending on the kind of thing they're doing. So that was a bit on data. Let me switch to what I would call computational workflows. This sort of how do you get from the idea that you want to try to do something to actually achieving it, and what are the barriers? Well, we've talked a bit about data. The other thing I'll talk about for a few minutes is sort of technology. What bits of technology? I've shown a few bits of this, but I think there's interface, there's ability to deploy this everywhere. So you kind of want to, you've built something. Can you deploy it, across, used to be just Windows, Mac, and Linux and things, right? But now it's not. It's mobile, and it's through the cloud, or it's locally, and then you have quite, on your mobile device, do you want to do it through the cloud, or do you want to do it locally running, and the rest of it? So there are many more sort of deployment issues, and those all have different optimizations, as of course you know. There's raw computational power. Are all the algorithms there? Do they work? Do they work cleanly? Are they powerful enough to do what you want? And then there's what I would call coherence. How much do you gain by having sort of one coherent setup versus lots of different setups? It's kind of like the Apple, going back to the Apple thing, we'll come back to Apple actually again, Apple versus Microsoft type of approaches and how those differ and kind of, whether binding things together gets you further than having things disparate with all pluses and minuses of those. And then I'll come on, then of course the other barrier is the human, which I'll mention a bit at the end. What have we been trying to do? We've been trying to build an infrastructure for injecting computation everywhere. That's kind of been the mission of of Wolfram Research for 30 years. It will be 30 years, actually on 23rd of June this year, since we launched, and actually the notable person who was at the launch was Steve Jobs, because we were bundled on his Next machines. If you remember Next machines, that happened between when Jobs was at Apple Round 1 and Apple Round 2. And it's always a rather nice anecdote I like, that the Next machine that's in the Science Museum that Tim Berners-Lee invented the web on, I think that was part of a group, and one of the reasons they bought that group of Next machines was because it had Mathematica bundled on it, so it's kind of a nice story I like to tell. One of the things that I think is interesting, I don't want to go through too much of this, but there is an interesting aspect to, I think, what we've tried to do, which is to build everything we do around symbolic expressions. So, what do I mean by that? I'm sorry it's a bit small here, but this is a table of data. But when you look at the code that represents that, it's a symbolic expression with stuff in it. If I do, lots of different types of things, a hierarchical list, same idea. Or a graph, same idea. Images, same idea. Documents, 3D graphics, they're all the same. And so what we've tried, and actually the most exciting perhaps is this interface. So the notebook that I'm doing this talk in is a symbolic expression. It's just a hunk of code. It's the same way as a computer. So we think of everything being the same entity. And that gives tremendous power to swap between things. Because you start thinking, I could write a piece of code to change all the bits of my notebook to be green. And it's just a piece of code to do that. It's a simple thing. It's not specially for notebooks. It's just a code that operates as if it was operating anywhere. So that gives tremendous power. And I think being able to build something in a consistent way is sort of important. Speaking of notebooks, notebooks have rather come of age. We hear lots about notebooks in the last year. We actually invented the computational notebook. On Next machines and Apple's, I can't remember which one came out first. The idea of these is to have a superset container of information, including code, which runs, which works, which you can present, which you can just work with. And as I said, this is a powerful sort of way of collecting your thoughts if you want to do technical things. It's no good really having a PDF because you kind of like, it's like it's dead. You want something that's live. And one of the things that's quite good is to marry that with a high-level style of language. So the idea you're putting language in the notebooks. And the language code represents two things. It's stuff you want the computer to do, but potentially it's also stuff you want to read. And people don't usually think of code that way, but code is a way to communicate technical ideas. Now, of course, if you're reading machine code, you have to be very specialized, and it's very low level, so you don't get very far very quickly. The trick is to have high enough level code that it's kind of readable enough that it's literate, is the normal terminology for this. And we've been trying to do this with Wolfram language, and I thought I might live dangerously and try to write you a little program here. So what I want to do, I thought it was the sort of stage in the talk where you might want not to see me anymore, so I thought I might block myself out. And so I'm going to do that by trying to set myself to be me, and then I want to show me at the same time as a graphics of a rectangle, and this is always harder when you're in front of people, by the way. It's like the presenters, as you said in the video. It's slightly harder than it seems. So what I'm going to do is apply a rectangle to finding my face, or any number of faces actually, in this, and then hopefully, if I have got my act together, we can block me out, like so. And there it goes. So my point about this is I happen to have written this in a rather colloquial form of code, but it's a fairly short program to do a fairly complicated thing that's meshing together, bits of graphics, rectangles, and identifying my face, sort of algorithms, and a structure of symbolic expression that's dynamically expressing itself in this notebook. And by the way, another thing just to mention about this notebook, well, I remember, actually, one of the reasons I was using the current version, this is a test version of our software, as I mentioned, is because we're using these new presenter tools, and this allows me to have toggled and things between different slides, and maybe I won't do that right now, actually. I'll do that at the end. I don't want to live too dangerously. Now, another part of what's important is, do you run stuff locally on a computer, or do you run it in the cloud? Do you run it on a public cloud? Do you have a private cloud? Our view is that in the end, you want a hybrid set of these things. None of them is best for everything. So we've been trying to build sort of computation as a service. Can you stick a private cloud and have it operate as a service? You know, it's not perfect to do that because, for example, a lot of things like I was just showing may run better locally. And so these are some of the examples of enterprise private clouds and things that we've been trying to do. One of the things we've been trying to do, but also I think is important, and actually I feel like this is less a message I have to give here than I do often in companies, with companies and industries. It's what I call computational siloing. You know, often in banks, I don't know why I'm picking on banks, but I will. In banks, you know, you have 5 departments who are basically doing quite similar computation in a quite similar way, all built totally separately, all with its own idiosyncrasies, none of it built terribly well. And actually they could have one, you know, they could think of it as a centralized sort of provision of computation for certain kinds of things. Now, I think universities on the whole have done that much better, actually, but you know, there's distance to go, particularly for some of the high-level computation that, you know, the physicists all go and use the computation anyway. The social scientists, the biologists, the linguists and things don't. And I think they could get much more access to this with sort of good to, you know, high-level things. And I often show this what I call a spike diagram, where you can imagine all of these silos. I guess we've been trying to submerge them all by kind of building them. And the key thing to know is, even if you have a particular silo, if you sit on it, it's rather sharp. But the point is, when you fall off and go to a slightly different area of computation, you tend to fall a long way down to ground. If you have tried to provide computation at a high level across the university, for example, it allows you to sort of operate at a high level in almost all cases. So what we've been doing in higher ed particularly is sort of powering computational thinking across educational research. That's what we'd like to do. We'd like to take the idea of computational thinking and, in a sense, empower everyone to do this. Now, that might be everyone in terms of the subjects, but it may also be everyone in terms of the administration to use computational data, thinking, etc., to be able to do this. And that's a whole range of things. You know, you need some ready-built content, you need maximum automation, as we talked about, and you need data. Okay, so that is a little bit on technology. I wanted to spend a few minutes now talking about the human. And what we have to do with the human to get them ready for this new AI age optimally. And I guess I'm talking to you about this from several points of view. Obviously, you are, in many respects, you know, in charge of setting up the technology and making things work for your universities and making sure they can do the right subjects and deploy those. But I think I also want to communicate for you to communicate this as well to others, as to really get people thinking, what is the subject matter? You're employers of many of the sorts of people who have technical skills. What is it that people should be learning now that computers do all these things I've been showing? And I think there are 2 ends of the spectrum to look at here that are important. One is what I call survival skills. You know, a few thousand years ago, I guess it was important to know how to light a fire to stop wild animals coming into your cave. That isn't today's normal survival skill, not in most parts of the country anyway. Maybe in Oxfordshire, but not so much elsewhere. The question is, what are they? And I think there are quite a few computational survival skills that you kind of can't really live properly. You know, you're going to get screwed on understanding your mortgage type of thing. That's a survival skill in a sense. But there are many others. But then there's the other end, which is the top end. What's the top value added that the human can give in this computational era? I don't think it's, you know, learning text by heart. I think it's somehow interacting with the machinery in a way that steps it up. And I guess what's interesting to me is that there is a core human skill, in my view, which I'm going to call computational thinking, that actually is important at both ends of the spectrum. It's kind of a thing everybody needs to know. Now, some people may only know it at a very basic level, some people know it at a very high level, but in the end, it's kind of a core societal issue. And the question is, how can we get people better at computational thinking? And the big question is, we have a core subject in schools right now, it's called maths. Is it preparing people appropriately for computational thinking? And my argument is no, really it isn't. Not in any country actually in the world, and I'm afraid we seem to be going slightly backwards here. Here's the point. I think maths or computational thinking is really a four-step process. And what you're really doing is you're defining a question. If I go on talking for too long, will I, and I hope I don't do this, and we locked all the thing down, we turned all the air conditioning off, how long will it be till we all suffocate? I hope I'm not going to test this. That would be a question I was defining. The next thing we're doing is we're abstracting it. We're taking it to maths. We're saying, okay, can I make a representation symbolically in a sense of this so that I can work out an answer? Why do we do that? Because the language of maths is really powerful for working out answers. We can talk about this in English, but in the end, we'll probably get less far with a definite answer than we will with hundreds of years of maths, computational experience. Then the third step is, you compute the answer. You say, I'm going to use this magical process. I'm going to go from the question I set to the answer. So maybe x equals 3. What does x equals 3 mean? Well, maybe we've got 3 hours or something. But the next step is to interpret that. That's really that step I just did. And also to interpret whether it's garbage or not. Is that rational? Did we do the calculation right? Here's what's going wrong in basically a decade of everyone's maths education. We're spending all our life learning how to hand calculate step 3. This doesn't make a lot of sense. Computers are billions of times better at step 3 than humans. What we ought to be doing is spending our life at school and things on steps 1, 2, and 4 and knowing how to employ computers to do step 3. And over the last 5 or so years, we've been building a thing called computer-based math to try and reimagine the maths curriculum, assuming computers exist. Now, it sounds funny. The fact is, nobody has done this in the world. It's rather shocking with all the billions of dollars and pounds and things poured into maths education. Nobody seems to have reimagined the subject. Lots of people reimagining how you present the existing subject, how you computerize the existing subject, but not how you change the fundamental subject. So just a very quick taste. We built rather nice modules. So this is some of the modules in computer-based maths. This one was actually built for the Irish, and so this is apparently the equivalent of the Tour de France cycling race. And this is an example of a notebook that I was talking about, deploying a teacher and a student edition of interest. So the orange boxes are for teachers only. And there's description on what you do and so forth, and I can go to the student version that's the same as this but without the orange boxes. And you can see that you can mix like interactive stuff here. This is how do you affect how fast you can go around the track or the route, and what affects cycling speed, the power you need for a given speed, and then there are a whole bunch of questions under here that get sent off to the teacher and so forth. So this is just an example, but the point is we're leading with a question. Question is of the whole module, how fast can I cycle around it? The question leads. The abstraction to maths is how you fulfill, how you try and answer the question. That's the way around it ought to be in education. Very quick, I'm just going to dart through this quickly, but how do you compare computational thinking, maths, coding? I would say computational thinking is a way to do STEM subjects and beyond, and life. I think maths is a particular domain knowledge of that, and coding is a way you express it. Very important to understand, coding, as I said before, is a way you write down ideas, as well as a way that you don't really write down ideas with traditional maths notation anymore. You do a bit, but really you write it as code. That's how you actually progress with computational thinking. So coding is important for that reason. Another problem that often comes up, people ask me, how do you fix motivation? We have so many people that are drained out of the system who might be perfectly good at what I'm talking about here, computational thinking, but are lost. I mean, the thing I think is the predominant idea here is start them with problems that relate to their life. Don't start them with some completely abstract thing that, can you solve x squared plus 2x plus 1? Well, maybe, but why do I care? I've never done it. By the way, it's one of the reasons I like to show that thing earlier. I love to ask government ministers particularly, when was the last time you solved a quadratic equation? And the answer is, well, maybe to help my children. Why are we teaching that predominantly and not some of these other problem-solving skills. So I think if you have messy, hard problems, not easy problems, hard problems, real problems they come across in their lives, and then you use mathematics and computation and computers to help them to get the answers to those problems, I think you're much more likely to have motivation, particularly among the people who might have switched off very early. You know, people from more academic backgrounds sometimes can switch on for longer to start with abstract ideas, and we lose many of the others very quickly. And we've actually, I won't show it now, but rather shockingly, we've gone around the world trying to find what are the outcomes people want from maths. Are they sensible? And the answer is, it's a pretty mixed bag of what people want. And we've been trying to reform, so we've got our own list of what we think are useful outcomes from computational thinking education. Back to Apple for a second. Steve Jobs at our launchpad gave a very nice quote that I only found again recently a few years ago, which is, Mathematica will revolutionize the teaching and learning of math by focusing on the prose of mathematics without getting lost in the grammar. And I've highlighted will. He was so right and yet so wrong. He should have said should. We're still waiting. And I guess that's the change we're trying to make with computer-based maths. How do we make it happen? There's a very stuck ecosystem around schools. Very hard. You've got to get assessments changed, and then the teachers have to agree with that, and then the parents and the governments and everybody else has to agree it in one go to make the change, is how it currently works. Result, not a lot of change happens. Very hard to get subjects to change at school. Particularly course subjects. If it's, I was amused with my daughter, if it's religious studies, that's actually metamorphosized quite far to more or less philosophy. But it's not a mainstream subject. So if it's mainstream and very important, you can't innovate the subject very much, is the problem. And particularly maths has gone through this fundamental change based on computers, can't innovate that very easily. Assessment is the linchpin of that, and I think it'll be very important over the coming years for us to try and establish alternatives to maths, A-levels and the like, as assessments, like a computer-based maths or computational thinking assessment. The reason I'm particularly mentioning it here is because, of course, the big driver for that is university entrance. And over time, a lot of universities come to me all over the time saying, oh yes, it's no good for our engineering course, no good for our physics course, no good for our biology course. People don't seem to know any maths. If we can get a voice together more centrally on the kind of maths that's really required around our thinking, around other people's thinking, and really voice that, then we'll get those sorts of qualifications we want so that we can get the right type of computer-based thinking, so to speak, computational thinking coming in. I think that'll help a lot when people get to universities. So I think the university has a huge role in this sort of change. My big message around this is, and to governments and others, is stand on the power of automation. I don't really need to give it to you guys, but stand on the power of automation. Don't try and pretend you're computers and try and make third-rate human computers. And what we want is first-rate human problem solvers. Don't compete with the machines, because you won't win. Step up from the machines and go to a further level. And one final thought on this before I wrap up. One of the problems we've had in this is the brand of maths toxic? Should we call it maths? Or is maths really quite a toxic word at this point? There are an awful lot of people, there are the maths people, some of whom will be here, including me, who enjoyed maths. But actually, as a brand, it's quite hard to sell, really, to most of the population. It's there, and it's big, but it's not particularly well received. And so one question is whether one calls it maths or one calls it computational thinking, or what one does with that. So I'm hoping I've given you some ideas to prepare for what I call the computational knowledge economy. So what that is, so to speak, the economy beyond the knowledge economy, where mixing computation and knowledge are sort of the predominant high-level thing. And I hope it gives you some ideas for your computation strategy, and hopefully leaves you more like this as I'm computing than it started out. Thanks very much indeed.
I'm absolutely fascinated, and I'm a bit scared of maths, but
good, you'll be a devotee then.
But I get the idea of the computational thinking, and that really sparked a few thoughts in my head. Have we got any questions for Conrad We have a couple of mics out there if anybody's got a question or two. Yep. One at the front here. I've lost... here he comes, John.
One at the back as well, so I don't know who we go first, but... Should we go back
I'll go
first since the mic has...
Mary first. Is it Mary? It's a very bright light here, so I can't see very well. So.
Hi, I was absolutely fascinated by your 4 steps of computational thinking, and the thing that occurred to me was step 1 being define the question, and step 4 being interpret the answer. That could apply to any discipline across the entire university curriculum. So is our challenge to make it possible for people to complete the middle 2 steps without being mathematicians?
Okay, so I think your question is a very interesting one, which is sort of applying this to all different subjects. See, the way I think about computational thinking is it's kind of a way of thinking about life. And, you know, and there are different ways of thinking about life. There's sort of theological ways and philosophical ways, and this is a new way, a newish way, which wasn't very useful outside very structured things. So it now is, as you point out. I mean, I think every subject should have a computational element to it, computational history. You know, analyze, when we did a word cloud thing, analyzing presidential speeches based on the modal word, you know, the biggest word in the speech, inaugural US presidential speeches. Yes, I mean, I'm going to slightly step with terminology that because what you're saying is, can everyone without maths, in quotes, and I'm amused by the way you use that, actually. It's a good way of using it. Can everyone without maths apply computational thinking or be taught to apply computational thinking to essentially all subjects? And I think, you know, to a greater and lesser extent, yes. That's kind of what I'm arguing for. And in fact, you have to go further than that because, in a sense, maths is a subject amongst very few that is considered at school to be compulsory for years of your life. It's, you know, a mainstream subject. There's kind of maths, there's kind of English if you're in England or Scotland or Wales or Northern Ireland and other places. You know, and most people have to do some history and things like that. But there are very few subjects in that category. Is it rational to have it in that category? Well, it isn't unless you're applying it to other subjects. If maths is just for its kind of its own right, then fine, it's like ancient Greek. You know, I mean, I enjoyed doing some ancient Greek, which I had to do, but yeah, I don't think everybody should have to learn ancient Greek. It doesn't seem very useful to me. If they happen to be very interested in ancient Greek, that's great. Off they go and do that, and I'm all for that. So I think maths, if it is to survive as a mainstream subject, has got to be applicable, but maybe it's better, in a sense as you did, not to call it maths and to say we need to apply these 4 steps. I do think the hardest step is the second step, abstraction. That's the thing that's really tricky. I find this tricky, right? And what's even, I mean, I'll just do one more 30 seconds on this. It's quite a complicated discussion, but the real mistake right now is when you abstract, you need to know the tool set you are abstracting to. Now, if the tool set you're abstracting to is quadratic equations and normal distributions, it's a pretty small tool set, and you're likely to not be able to abstract anything very interesting very far. If you are abstracting to a huge tool set of our modern computational tools, machine learning, all the other things we talked about, you are likely to be able to get much further. But you need to know what those are, and you need to learn those, and you need to get a feel for those. And so that's part of what should be happening. And so our education is completely the wrong way round for that. And that makes the abstraction actually harder and much less effective. Enough on that for the moment. Thanks.
Question in the front here, I think. Sorry, I've lost sight of it, John.
Hi.
Oh, sorry.
Hi.
Over here first.
I've just moved from the university sector into the college sector, so I'm really pleased that we're able to be here today. But I was interested in your idea that universities are going to play a key role in this change, moving from maths to computational thinking, or whatever we end up calling it. What do you think is the key role for colleges in the college sector?
The key role for
colleges?
I mean, there are several steps I see this. I think the first step is, at the moment, 80% of the problem is total confusion. Right? And what I mean by this, and I find it a bit shocking, and to be fair, I was pretty confused about it still. I spent 10 years thinking about it, right? I mean, a lot of people complain, even technical people, but they haven't really understood what the core issue is, which is the machinery of doing the calculations changed from humans to computers. Totally, fundamentally, at a greater extent than any other revolution of that sort that one can think of in history. And so one kind of needs to reform everything on that. So I think one part of this is to, in a sense, message and make sure people understand that possibility. And I don't know the best way to do that. I think a second one is obviously to have the right technology to be able to support that, which I don't think is too hard to arrange. I mean, lots of technology that supports this pretty well. I'm sure you already have it. And I think I think holding a lot of discussions with these departments about what could really drive the use of the computation forward is a good way to make that work. But I might want to think about that a bit further, actually. It's a good question, and I'm not sure I've completely crystallized a good answer. Maybe other people have a good suggestion for that as well.
You talked a lot about the tools and things like that. One of the things that quite often drives use of tools is application. And what I'd be interested to know about is in terms of your conversations around, you know, changing the maths curriculum, moving away from the concept of maths to computational thinking. Have we thought about how you could then use the application of that as a driver for that change, and what sort of things do you see happening in that space?
Yeah, okay, it's a great question. I totally agree with you. Applications are a great driver, and in fact, I have this problem in our company often because I ask for things called, again, back to jobs and things, I have things called pivotal examples. What is the pivotal example we need to demo, often of our technology, but the same thing applies to maths, that really kind of excites people? And it's quite hard actually to come up with those in sort of, so, I mean, in a sense, what we've been trying to do with computer-based maths is to do that. We've been trying to think of question sets that will help people sort of, they seem excited about. I mean, one we're working with the Estonians actually, a country that is rather ahead on this. And, you know, we had a question set, are girls better at maths? So we thought teenagers might find this kind of interesting. You know, I'm a girl, I'm a boy. Who's better? Well, give them all the data from Estonia's exams and everything else. What's the question mean? I don't know. More girls, fewer girls take maths. Are they better or worse when they take it? You know, can the girls game the answer to be different to the boys? I mean, there are lots of quite deep questions there. But something that, so I think one of the things is to, I think there are two parts to this. One is that a lot of people thinking about the content actually don't know much about the technology, and they have no, you know, they're sort of 20 years behind in what was possible. So I think having sort of pivotal technological examples of what one can do is pretty helpful, just to showcase that. I think the other side of it is thinking up places where you can show nice, often graphical outputs, and to start with that and work back to how you got there, so to speak. I mean, we've got one. We've got a thing called the Demonstrations Project, which has, I don't know, 11,000 things on it now, which shows sort of interactive applications done with this. And I mean, that's just one example. There are others. But I think that's quite helpful in getting people engaged with code. So again, not a complete answer, but I totally agree with the thrust of the question. And again, as much as we can help with that, we'd love to do that. And you know, we're not as organized as we might be sometimes, but do ask us if you would like an example in different areas, for example, you know, biological example or something. Great.
Well, I'm very conscious of time, everybody. The partner case studies are about to start shortly, so I'd like us to thank Conrad for a really interesting presentation and answering our questions.
Thank you very much. And I'll just say, actually, I'll be around for a few hours now, and also my colleague Andrew Pollard is somewhere just over there if you have any other questions as well, if you can't find me. Thanks very much indeed.
Oh, I suspect there might be a queue for that. Thanks very much, everybody, and we'll see you after the partner